I will start with something that might surprise you. The speed of light was one of the first things humans ever measured about the universe with real precision. For most of history, people assumed light traveled instantaneously. When you opened your eyes, you saw everything immediately, right? It seemed obvious that light didn't need time to travel. But in 1676, a Danish astronomer named Ole Rømer noticed something odd while studying Jupiter's moons. The moons seemed to run ahead of schedule when Earth was closer to Jupiter and behind schedule when Earth was farther away. The only explanation that made sense was that light took time to cross the extra distance. From these observations, Rømer calculated that light traveled at a finite speed. His estimate was about 140,000 miles per second, remarkably close to the true value considering the limited tools of his time. This discovery was revolutionary, but it was only the beginning. Over the next centuries, scientists refined their measurements of light speed using increasingly clever methods. By the late 1800s, physicists like Albert Michelson had measured the speed of light to incredible precision. But these precise measurements led to a puzzle that would shake the foundations of physics. Here's where things get weird. According to everything scientists knew about motion, speeds should add up in a straightforward way. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground should see the ball moving at 80 miles per hour. This is just common sense, right? But light doesn't follow this rule. The Michelson-Morley experiment in 1887 tried to detect differences in light speed as Earth moved through space. Earth orbits the Sun at about 67,000 miles per hour, so light moving in the same direction should seem faster than light moving the opposite way, but that's not what they found. No matter which direction they measured, no matter what time of year, light always traveled at exactly the same speed. This result was so shocking that many physicists refused to believe it. They invented elaborate theories about invisible substances called ether that supposedly carried light waves. But every attempt to salvage the old understanding failed. Light's speed was constant, period. It didn't care about your motion, Earth's motion, or anything else. Enter Albert Einstein, a 26-year-old patent clerk with a wild idea. In 1905, Einstein published his special theory of relativity, which started with two simple assumptions. The laws of physics are the same for all observers moving at constant speeds, and the speed of light in a vacuum is the same for all observers, regardless of their motion. From these two principles, Einstein derived consequences that seem to defy common sense. Time slows down for objects moving at high speeds. Lengths contract in the direction of motion. Mass and energy are equivalent, related by the famous equation E equals mc squared. And most importantly for our story, nothing with mass can ever reach the speed of light. To understand why, you need to grasp something fundamental about what happens as you approach light speed. Let's say you're in a spacecraft with an incredibly powerful engine. As you accelerate, something strange happens. The faster you go, the more energy it takes to increase your speed even a tiny bit more. At everyday speeds, this effect is negligible. Doubling your speed roughly doubles the energy needed, but as you approach the speed of light, the energy requirements explode toward infinity. At 50% the speed of light, you'd need about 15% more energy than Newton's laws would predict. At 90% the speed of light, you'd need more than double. At 99%, you'd need 7 times more. At 99.9%, you'd need 22 times more. The pattern is clear and merciless. The closer you get to light speed, the more energy you need for each additional mile per hour. To actually reach the speed of light, you would need infinite energy. Not just a lot of energy, literally infinite energy. Since the universe contains only a finite amount of energy, reaching light speed is impossible for anything with mass. But why does this happen? The answer lies in the nature of space and time themselves. Einstein showed that space and time aren't separate, fixed stages where events happen. Instead, they're aspects of a four-dimensional fabric called spacetime. When you move through space, you're also moving through time, and your total speed through spacetime always equals the speed of light. Think of it this way: when you're sitting still, all of your motion is through time. You're traveling into the future at 1 second per second, but when you start moving through space, some of that motion gets diverted. The faster you move through space, the slower you move through time. This is why time dilation happens. It's not a malfunction or illusion, but a fundamental feature of how space-time works. This cosmic speed limit isn't arbitrary, it's built into the geometry of space-time itself. Asking why nothing can go faster than light is like asking why you can't draw a square circle. It's not a rule imposed from outside, it's part of what space and time mean. The evidence for this cosmic speed limit comes from countless experiments and observations. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.9999% the speed of light. Despite using energies that could power a small city, they can't push particles that final tiny fraction to reach light speed. The particles gain energy, but instead of going faster, they become more massive, exactly as Einstein predicted. GPS satellites provide everyday proof of these effects. These satellites orbit Earth at high speeds and experience less gravity than we do on the surface. Both effects cause their clocks to run at different rates than Earth clocks. Without corrections for these relativistic effects, GPS would accumulate errors of about 6 miles per day. The fact that GPS works is proof that Einstein's speed limit is real and affects your daily life. Cosmic ray particles provide even more dramatic evidence. These high-energy particles, created in violent cosmic events, slam into Earth's atmosphere at speeds incredibly close to the speed of light. Some have energies millions of times greater than anything we can create in laboratories. Yet even with these enormous energies, they never exceed light speed. The universe's most powerful particle accelerators, exploding stars, colliding galaxies, feeding black holes, all respect the cosmic speed limit. But here's where things get even more interesting. The speed of light isn't really about light at all. It's the speed of causality, the maximum rate at which cause and effect can propagate through space. Light happens to travel at this speed because photons have no mass. But the deeper truth is that information itself cannot travel faster than this cosmic limit. This connection between the speed of light and causality leads to one of the most mind-bending implications of Einstein's theory. If you could somehow travel faster than light, you wouldn't just be breaking a speed limit, you'd be traveling backward in time. This isn't science fiction, it's a direct mathematical consequence of how space-time works. To understand why, imagine you have a friend on a distant planet 4 light-years away. If you could send a message faster than light, say in just 1 year, here's where things get weird. From the perspective of someone traveling at high speed relative to you and your friend, your instantaneous message would arrive before it was sent. They would see effect preceding cause, which would allow for paradoxes like sending a message to your past self telling you not to send the message in the first place. The universe seems to have a built-in protection against such paradoxes. The speed of light creates what physicists call a light cone, a boundary in space-time that separates events that can causally influence each other from those that cannot. Your future light cone contains all the events you could possibly influence. Your past light cone contains all the events that could have influenced you. Events outside these cones are in what's called elsewhere, regions of space-time that cannot interact with you without exceeding light speed. This structure of space-time with its built-in speed limit isn't a bug, it's a feature. It ensures that cause always precedes effect, that the universe maintains logical consistency and that reality unfolds in an orderly way. Without this cosmic speed limit, the universe would be a chaotic mess, where effects could precede causes and the very notion of before and after would break down. But wait, you might be thinking, haven't you heard about things that do travel faster than light? What about quantum entanglement, where particles seem to influence each other instantaneously across vast distances? Or the expansion of space itself, which can carry galaxies apart faster than light? These are excellent questions that reveal the subtle nature of the cosmic speed limit. Let's tackle quantum entanglement first. When two particles are entangled, measuring one does instantly affect the other, no matter how far apart they are. Einstein called this spooky action at a distance and was deeply troubled by it. Modern experiments have confirmed that this correlation is real and does happen faster than light could travel between the particles. But here's the crucial point. While the correlation is instantaneous, you can't use it to send information faster than light. The results of measurements on entangled particles are random. Only when you compare the results, which requires normal, slower-than-light communication, do you see the correlation. Quantum entanglement is like having two coins that always land on opposite sides, no matter how far apart they are when flipped. The correlation is real, but you can't use it to send a message. As for the expansion of space, this is indeed happening faster than light for sufficiently distant galaxies. But this doesn't violate the cosmic speed limit because the galaxies aren't moving through space faster than light. Space itself is expanding between them. It's like dots on an inflating balloon moving apart without actually moving across the balloon's surface. The speed limit applies to motion through space, not to the expansion of space itself. Speaking of cosmic mysteries, if you're fascinated by how space itself can expand, you'll be amazed by what might exist beyond the boundaries of our observable universe. In my video called What Lies Beyond the Edge of the Universe, I explore mind-bending possibilities from infinite cosmic expanses to parallel universes and higher dimensions. Check out the link in the description to continue your journey into the greatest cosmic questions. Now back to our exploration of the cosmic speed limit. These subtleties highlight something profound. The universe's speed limit is more sophisticated than a simple rule saying, "Nothing goes fast." It's a fundamental principle about the nature of information, causality, and the structure of space-time itself. Now let's explore what actually happens when you push against this cosmic speed limit. The effects are far stranger than science fiction, yet they're confirmed by countless experiments and observations. Understanding these effects will show you why the speed of light isn't just a barrier to be overcome, but a fundamental feature that shapes reality itself. Time dilation is perhaps the most famous effect. As you approach the speed of light, time literally slows down for you relative to the rest of the universe. This isn't an illusion or a measurement error. Time itself flows at different rates for objects moving at different speeds. The mathematics is beautifully simple. At half the speed of light, time passes about 87% as fast as normal. At 90% light speed, time passes at 44% normal rate. At 99%, it's down to 14%. At 99.9%, time crawls by at just 4.5% its normal rate. This has been confirmed by countless experiments. In 1971, physicists Haffel and Keating flew atomic clocks around the world on commercial airliners. When compared to reference clocks on the ground, the flying clocks had aged slightly less, by exactly the amount Einstein's equations predicted. The effect was tiny at airplane speeds, just nanoseconds, but it was real and measurable. Particle accelerators provide more dramatic confirmation. Unstable particles called muons are created when cosmic rays hit Earth's atmosphere. These muons have a very short lifetime, about 2.2 microseconds. At that rate, even traveling at near light speed, they should decay before reaching Earth's surface. But we detect them at ground level all the time. Why? Because at their high speeds, time dilation stretches their lifetime from our perspective, giving them time to complete the journey. From the muon's perspective, something equally strange happens. To the muon, its lifetime is still 2.2 microseconds, but the distance to Earth's surface has contracted due to length contraction, another relativistic effect. The muon sees a much shorter journey which it can complete in its brief lifetime. Both perspectives are equally valid and give the same result. The muon reaches Earth's surface. This length contraction is just as real as time dilation. As you approach light speed, distances in your direction of motion literally shrink. At 90% light speed, distances contract to 44% of their original length. At 99.9%, they shrink to just 4.5%. Imagine you're traveling to Proxima Centauri, the nearest star to our Sun, about 4.2 light-years away. At 99.9% the speed of light, the journey would take about 4.2 years from Earth's perspective. But from your perspective aboard the spacecraft, the distance would contract to just 0.2 light-years, and the journey would take only 2.4 months. You would age 2.4 months, while Earth aged 4.2 years. This isn't a trick or illusion. Both time measurements are real, there's no correct frame of reference. This is the profound insight of relativity. Space and time are not absolute but depend on your motion. The universe doesn't have a master clock or a preferred ruler. Every observer's measurements are equally valid. These effects lead to the famous twin paradox. Imagine identical twins where one stays on Earth while the other travels to a distant star at near light speed. When the traveling twin returns, they'll have aged much less than their Earth-bound sibling. If the journey involved speeds of 99.9% light speed to a star 20 light-years away, the traveling twin would age about 1.8 years, while the Earth twin aged 40 years. This isn't theoretical, it happens every day in particle accelerators and with cosmic rays. We've observed particles living far longer than they should because of time dilation. In a very real sense, approaching light speed is a form of time travel to the future. The faster you go, the more you can skip ahead in time relative to the rest of the universe. But there's a price for this temporal shortcut: mass-energy equivalence. As you approach light speed, your relativistic mass increases. This doesn't mean you're gaining atoms or getting bigger. Instead, the energy of your motion manifests as increased resistance to further acceleration, what physicists call inertial mass. At everyday speeds, kinetic energy follows the familiar formula from high school physics: 1/2 mass times velocity squared. But at high speeds, the real formula involves the Lorentz factor, which approaches infinity as you approach light speed. This is why particle accelerators need exponentially more energy to push particles incrementally closer to light speed. The Large Hadron Collider provides a perfect example. It accelerates protons to 99.99999% the speed of light. At this speed, each proton has about 7,000 times its rest mass worth of kinetic energy. The LHC uses enough electricity to power a small city, yet it can only push particles to within a tiny fraction of light speed, never reaching it. This brings us to one of the most profound insights about the cosmic speed limit. Mass and energy are fundamentally the same thing, related by Einstein's famous equation E equals mc squared. The c in this equation isn't just the speed of light, it's the conversion factor between mass and energy, the fundamental constant that relates space to time. When you heat up a cup of coffee, it actually becomes slightly more massive due to the added thermal energy. When the sun fuses hydrogen into helium, the mass difference converts to energy according to E equals mc squared. Every chemical reaction, every biological process, every thought in your brain involves tiny conversions between mass and energy governed by this cosmic constant. This is why the speed of light is so special. It's not just a speed limit, it's the fundamental constant that defines the relationship between space and time, between mass and energy, between cause and effect. It's woven into the fabric of reality at the deepest level. But what about those science fiction stories about warp drives and wormholes? Don't they offer ways around the cosmic speed limit? The surprising answer is that some of these concepts are theoretically possible within Einstein's equations, but they come with catches that make them practically impossible or paradoxical. Let's start with wormholes. In 1935, Einstein and his colleague Nathan Rosen discovered that the equations of general relativity allow for bridges connecting distant regions of space-time. These Einstein-Rosen bridges, or wormholes, could in principle allow travel between distant parts of the universe without exceeding the speed of light locally. The key word here is locally. A wormhole doesn't let you travel faster than light. It provides a shortcut through space-time. Imagine an ant walking on a piece of paper. If the paper is flat, the ant must walk the full distance between 2 points, but if you fold the paper so the 2 points touch, the ant can step across instantly. The ant never exceeds its maximum walking speed, it just takes advantage of the paper's geometry. But here's the catch. Wormholes that could actually be traversed would require exotic matter. With negative energy density, something that has never been observed and might not exist. Even if traversable wormholes could exist, they would likely be incredibly unstable. The moment anything tried to pass through, they would collapse faster than light could cross them. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics somehow prevent the creation of time machines. Every theoretical method of faster-than-light travel or time travel seems to have a built-in flaw that makes it impossible. It's as if the universe has a security system against paradoxes. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, offers another theoretical loophole. This concept involves contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that carries the ship faster than light relative to distant observers. The ship itself never exceeds light speed within its local bubble of space. But again, there are devastating problems. The Alcubierre drive would require enormous amounts of exotic matter, by some calculations, more than the mass energy of the entire observable universe. It would also create causality paradoxes, allowing for time travel into the past. And recent research suggests that even if you could create such a drive, you couldn't control it. You'd be causally disconnected from the front of the warp bubble. These theoretical possibilities teach us something important. The universe's speed limit is more subtle and more fundamental than a simple prohibition. It's not that the universe has a rule against going fast. Rather, the structure of space-time itself makes faster-than-light travel logically inconsistent with causality. Let's talk about tachyons, hypothetical particles that always travel faster than light. The mathematics of relativity doesn't actually forbid such particles from existing. In fact, the equations work perfectly well for particles that always travel faster than light, just as they do for particles that always travel slower than light. But tachyons would have bizarre properties. They would have imaginary mass in the mathematical sense of involving the square root of -1. They would speed up when they lose energy and slow down when they gain energy. Most problematically, they could be used to send signals into the past, creating causality paradoxes. Despite decades of searching, no experiment has ever detected a tachyon. Most physicists believe they don't exist and that their absence is another example of the universe's protection against paradoxes. The cosmos seems to be constructed in a way that preserves the logical flow of cause and effect. This brings us to a deep question. Why does the universe have this particular speed limit? Why 186,282 miles per second and not some other value? The answer touches on the fundamental nature of reality itself. The speed of light is related to two other fundamental constants, the permittivity and permeability of free space. These constants determine how electric and magnetic fields behave in a vacuum. Maxwell's equations, which describe electromagnetism, show that electromagnetic waves, including light, must travel at a speed determined by these constants. But this just pushes the question back a level. Why do the permittivity and permeability of space have the values they do? This is part of a larger mystery in physics. Why do the fundamental constants of nature have the specific values we observe? Some physicists invoke the anthropic principle, the idea that we observe these particular values because they're compatible with our existence. If the speed of light was significantly different, the universe might not be able to form stars, planets, or life. We find ourselves in a universe with this particular speed limit because universes with different values wouldn't have observers to measure them. Others speculate about a multiverse where different regions have different fundamental constants, including different speed limits. We would naturally find ourselves in a region where the constants allow for complex structures and life. But these ideas remain highly speculative and perhaps untestable. What we do know is that the speed of light is intimately connected to the structure of space-time itself. In Einstein's theory, space and time are unified into space-time, and the speed of light is the conversion factor between space and time. Asking why light travels at this particular speed is like asking why there are 3 feet in a yard. It's a fundamental part of how we measure the universe. The cosmic speed limit also plays a crucial role in quantum field theory, our most successful framework for understanding particles and forces. In this theory, particles are excitations in quantum fields that fill all of space. The speed of light determines how these field disturbances propagate, setting the maximum rate at which particles can influence each other. Virtual particles, temporary fluctuations in quantum fields, can seem to violate the speed limit, but only within the constraints of the uncertainty principle. The more they exceed light speed, the shorter their existence must be. The universe allows these brief violations as long as they average out to respect the cosmic speed limit. This quantum perspective reveals another facet of why nothing can exceed light speed. Doing so would violate the fundamental quantum structure of reality. Faster-than-light particles would create inconsistencies in quantum field theory, leading to nonsensical predictions like negative probabilities. The speed of light also determines the strength of electromagnetic interactions. If light traveled faster, electric and magnetic forces would be weaker. If it traveled slower, they would be stronger. The particular value we observe allows for the rich chemistry that makes life possible. Atoms can form stable bonds, molecules can have complex structures, and information can be stored and processed in biological systems. Speaking of information, the cosmic speed limit applies not just to matter and energy, but to information itself. No signal, no message, no influence of any kind can propagate faster than light. This limitation shapes everything from computer design to the search for extraterrestrial intelligence. When you send a text message to someone on the other side of Earth, it travels through electromagnetic signals that move at light speed. The delay is tiny and about 67 milliseconds to go halfway around the planet, but it's there. For communication with spacecraft exploring the solar system, the delays become noticeable. A signal to Mars takes between 4 and 24 minutes, depending on the planet's positions. For interstellar distances, the limitation becomes profound. A conversation with someone at Proxima Centauri would involve a minimum 8.4-year round-trip delay. This cosmic speed limit doesn't just make interstellar travel difficult, it makes interstellar civilization as we imagine it nearly impossible. Any galactic empire would be limited by the speed of light, taking years or centuries for messages to cross between star systems. But here's a beautiful thought. The same speed limit that isolates us also connects us. When you look at the night sky, you're seeing the universe's history written in light. That star you're looking at might be 10 light-years away, meaning you're seeing it as it was 10 years ago. That galaxy might be 1,000,000 light-years distant, showing you a 1,000,000-year-old image. By the way, if you are enjoying the video, please consider giving a thumbs up and subscribing. I am starting now on YouTube, and your help really means a lot to me. Let's continue. The cosmic speed limit turns the universe into a vast time machine. The farther out you look, the further back in time you see. The most distant galaxies visible to our telescopes show us the universe as it was over 13 billion years ago when the first galaxies were forming. We can literally see cosmic evolution happening by looking at objects at different distances. This cosmic time machine effect has profound implications for astronomy and cosmology. When the James Webb Space Telescope captures images of the most distant galaxies, it's not just seeing far away, it's seeing far back in time. Those ancient galaxies appear as they were when the universe was young, allowing us to directly observe how galaxies formed and evolved. The finite speed of light also means that the observable universe has a boundary, not in space, but in time. We can only see objects whose light has had time to reach us since the Big Bang 13.8 billion years ago. Beyond this cosmic horizon lies the unobservable universe, forever hidden from our view not by distance, but by the finite age of the universe and the cosmic speed limit. This limitation might seem frustrating, but it's also protective. If light traveled infinitely fast, the night sky would be infinitely bright. Every line of sight would eventually hit a star, and their combined light would incinerate everything. The finite speed of light combined with the universe's expansion and finite age gives us the dark night sky that allows life to exist. The speed of light also shapes how we understand gravity. In Newton's theory, gravity acted instantaneously across any distance. If the sun suddenly vanished, Earth would immediately fly off in a straight line. But this instant action at a distance troubled physicists, including Newton himself. Einstein's general relativity solved this puzzle by showing that gravity isn't a force, but the curvature of spacetime. Changes in this curvature propagate at the speed of light. If the sun vanished, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth. Only then would Earth feel the gravitational change and fly off into space. This prediction was spectacularly confirmed in 2017 when the LIGO and Virgo detectors observed gravitational waves from colliding neutron stars. Telescopes also saw the light from this collision. Despite traveling 130 million light-years, the gravitational waves and light arrived within seconds of each other, confirming that gravity and light travel at the same cosmic speed limit. Speaking of cosmic mysteries, if you're fascinated by what might exist beyond our universe, you'll be amazed by what might have existed right here on Earth before humans. Could an advanced civilization have thrived millions of years ago? I explore this mind-bending NASA theory in my video, What If We Are Not the First Civilization on Earth? Link in the description. Now back to our journey through the cosmic speed limit. The universality of this speed limit reveals something profound about the nature of space and time. They're not just a passive backdrop for events. They're dynamic, interconnected aspects of a unified space-time. The cosmic speed limit is the thread that weaves space and time together into the fabric of reality. This interconnection shows up in surprising places. Take the simple act of moving your hand. When you decide to move, the signal travels from your brain down your nerves as an electrical impulse. These nerve signals travel much slower than light, about 200 miles per hour, but they still obey the cosmic speed limit. The electrical fields that carry the signal propagate at light speed, even though the signal itself moves much slower due to the biology of neurons. Even your thoughts are constrained by the cosmic speed limit. The electrical and chemical signals in your brain can't exceed light speed. This might seem like a trivial limitation, but some scientists speculate it places fundamental constraints on consciousness and intelligence. No matter how advanced a brain or computer might be, its processing speed is ultimately limited by how fast signals can travel between its parts. This brings us to an interesting question about artificial intelligence and advanced civilizations. Could an advanced AI or alien intelligence find ways around the cosmic speed limit? The answer appears to be no. Any information processing system, whether biological or artificial, must obey the same fundamental laws of physics. In fact, the speed of light places hard limits on computation. There's a maximum rate at which any physical system can process information, known as the Bremerman limit. This limit exists because computation requires energy, and the speed of light limits how quickly energy can be moved around. Even a computer the size of Earth, using all available energy optimally, couldn't exceed this computational speed limit. The cosmic speed limit also shapes the ultimate fate of the universe. As the universe expands and accelerates, distant galaxies are moving away from us faster and faster. Eventually, they'll be receding so fast that their light can never reach us. The observable universe will shrink and distant galaxies will fade from view, not because they cease to exist, but because the expansion of space carries them beyond our cosmic horizon. In the far future, trillions of years from now, our local group of galaxies will be alone in an empty, dark universe. All other galaxies will have passed beyond the cosmic horizon. Future civilizations in this era might have no way to know about the Big Bang or the universe's expansion. The evidence will have literally disappeared beyond the speed of light. This cosmic isolation highlights another aspect of the speed limit. It doesn't just constrain motion through space, but also the flow of information and causality. Regions of the universe that move apart faster than light become causally disconnected. They can no longer influence each other in any way. It's not just that communication becomes impossible, any form of interaction or influence is cut off. But let's bring this back to your daily life. How does the cosmic speed limit affect you personally? In more ways than you might think. Every time you use GPS, you're relying on corrections for relativistic effects. Every time you undergo a PET scan, you're benefiting from our understanding of antimatter, which exists because of the symmetries required by the cosmic speed limit. The electronics in your smartphone rely on quantum mechanics, which is intimately connected to the speed of light. The chemistry of your body, the stability of atoms, the energy from the sun, all depend on the particular value of the cosmic speed limit. If it were different, you wouldn't exist. Even your perception of reality is shaped by the finite speed of light. When you look at your hand, you're seeing it as it was a few nanoseconds ago, the time it took light to travel from your hand to your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun appears as it was 8 minutes ago. Everything you perceive is slightly in the past. This delay is usually negligible in daily life, but it becomes significant for modern technology. High-frequency traders worry about the milliseconds it takes signals to travel between stock exchanges. Online gamers experience lag due to the finite speed of internet signals. Even conversations on cell phones have a slight delay as signals bounce off satellites or travel through fiber optic cables. The cosmic speed limit also influences how we think about the future of humanity. If we ever become an interstellar species, we'll have to accept that it will take years or decades to travel between stars. There's no warp drive coming to save us. Any interstellar civilization will be shaped by the cosmic speed limit, with colonies separated by years of travel time. Some futurists propose generation ships, spacecraft where multiple generations live and die during the journey between stars. Others suggest sending frozen embryos or digital uploads of human consciousness. But all these proposals must respect the cosmic speed limit. There's no shortcut, no cheat code, no way around this fundamental constraint. Yet this limitation also protects us. The same cosmic speed limit that prevents us from quickly reaching the stars also protects us from cosmic dangers. Gamma-ray bursts, supernovae, and other cosmic catastrophes can't affect us faster than light speed. We always have warning time equal to our distance from the threat divided by the speed of light. The cosmic speed limit even shapes the search for extraterrestrial intelligence. Any alien signals we detect will be old, perhaps centuries or millennia old by the time they reach us. Any conversation with an alien civilization will involve decades or centuries between messages. The cosmic speed limit ensures that first contact, if it ever happens, will be a slow, patient process, not the dramatic encounter often portrayed in science fiction. This cosmic speed limit also has profound philosophical implications. It tells us something fundamental about the nature of reality and our place in it. The universe isn't just constrained by this limit, it's defined by it. The speed of light isn't merely a property of light, it's a property of space-time itself, a fundamental constant that shapes everything from the behavior of particles to the evolution of galaxies. Let's dive deeper into the quantum realm, where the cosmic speed limit takes on even more fascinating aspects. Quantum field theory, our most successful framework for understanding particles and forces, incorporates the speed of light at its core. The uncertainty principle, which states that you can't simultaneously know a particle's position and momentum with perfect precision, is intimately connected to the cosmic speed limit. When virtual particles briefly pop into existence from the quantum vacuum, they can temporarily borrow energy as long as they repay it quickly enough. The more energy they borrow, the faster they must repay it. This relationship is governed by the speed of light. If particles could exceed light speed, this delicate quantum accounting would break down, leading to logical contradictions and violations of energy conservation. The quantum vacuum itself, the seemingly empty space that fills the universe, is constantly bubbling with these virtual particles. Pairs of particles and antiparticles appear and annihilate each other within tiny fractions of a second. The speed at which these fluctuations can propagate through space is limited by the cosmic speed limit, creating a sort of quantum foam that gives space its fundamental structure. This quantum foam might be the deepest level of reality we can access. At the incredibly tiny Planck length, about 10 to the negative 35 meters, the fluctuations become so energetic that space and time themselves break down into a seething quantum soup. At this scale, the concepts of before and after might lose meaning entirely. The cosmic speed limit helps protect us from this chaos by smoothing out these fluctuations at larger scales. Some cutting-edge theories suggest that space and time aren't fundamental, but emerge from deeper quantum processes. In these approaches, the speed of light emerges as a collective property of the underlying quantum reality. similar to how temperature emerges from the average motion of molecules. The cosmic speed limit might be nature's way of maintaining causal order in a universe built from intrinsically chaotic quantum foundations. Loop quantum gravity, string theory, and other approaches to quantum gravity all must grapple with the cosmic speed limit. Any viable theory of everything must explain why this particular speed exists and how it shapes the universe at all scales. The fact that the same speed limit applies to everything from quantum particles to gravitational waves suggests a deep unity in nature's laws. This unity extends to the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Although these forces appear very different in our everyday world, physicists believe they were once unified in the extreme conditions of the early universe. The cosmic speed limit played a crucial role in how these forces separated as the universe cooled, helping to determine the fundamental structure of reality. In the first fractions of a second after the Big Bang, the universe expanded faster than light in a process called inflation. This doesn't violate the cosmic speed limit because, again, it was space itself expanding, not objects moving through space. This period of inflation helps explain why the universe appears so uniform on large scales and why it has the exact amount of flatness we observe. Some cosmologists propose that inflation is eternal, continuously creating new bubble universes in an ever-expanding multiverse. Each bubble might have different physical laws and different values for fundamental constants, including the speed of light. In this view, our particular cosmic speed limit is just one possibility among many, and we find ourselves in a universe with this specific value because it allows for complex structures like stars, planets, and life. This brings us back to the anthropic principle, the idea that we observe the particular physical laws and constants we do because they're compatible with our existence. If the speed of light was significantly different, atoms might not be stable, chemistry might not work, or stars might not form. We find ourselves in a universe with this particular speed limit because universes with different values wouldn't have observers to measure them. The cosmologist Brandon Carter, who coined the term anthropic principle, distinguished between two versions: the weak anthropic principle, which simply states that what we observe must be compatible with our existence, and the strong anthropic principle, which suggests the universe must allow for observers. The weak version is widely accepted as logical, while the strong version remains controversial among scientists. Whatever the ultimate explanation for the cosmic speed limit, its consequences ripple through every aspect of our understanding of reality. It connects the largest scales of the cosmos to the smallest quantum fluctuations, providing a unifying thread that helps make sense of our complex universe. The consistency of this speed limit across all known phenomena is one of the most impressive validations of modern physics. From laboratory experiments to astronomical observations, from particle accelerators to gravitational wave detectors, every test confirms that the speed of light is truly universal. This consistency gives us confidence that we're uncovering something fundamental about reality, not just an accidental feature of our corner of the cosmos. The search for potential variations in the speed of light continues, however. Some theories suggest it might have been different in the early universe or might vary in extremely strong gravitational fields. The variable speed of light, VSL theory, proposed by physicists João Magejo and Andreas Albrecht, suggests that light might have traveled faster in the very early universe, potentially solving some cosmological puzzles. But so far, no convincing evidence for variation has been found. Observations of distant quasars whose light has been traveling for billions of years show the same spectral patterns we see in laboratory experiments today, suggesting the speed of light hasn't changed significantly over cosmic history. The constancy of the speed of light is so fundamental to modern physics that it's built into the very definition of our units of measurement. Since 1983, the meter has been defined as the distance light travels in a vacuum in 1,299,792,458 of a second. We no longer define the speed of light in terms of meters and seconds, we define the meter in terms of the speed of light and seconds. This redefinition reflects a profound shift in our understanding. The speed of light isn't just another measurement, it's a fundamental property of spacetime that we use to calibrate our other measurements. It's more like a conversion factor between space and time than a speed in the conventional sense. Philosophers of science note that this makes the constancy of the speed of light somewhat tautological, true by definition. But the deeper truth is that the world behaves in a way that makes this definition useful and consistent with all our observations. The universe really does have this structure regardless of how we choose to describe it. This brings us to a fascinating question. Is the cosmic speed limit the same everywhere in the universe? According to Einstein's theory of general relativity, the local speed of light is always the same. But the curvature of space-time due to gravity can affect how light travels over large distances. Near a black hole, for instance, light paths are dramatically curved, creating effects like gravitational lensing. From the perspective of a distant observer, light seems to slow down as it passes through a gravitational field, but locally, at each point along its path, light always travels at exactly the same speed. The apparent slowing is due to the stretching of space-time itself, not an actual change in light's fundamental speed. This constancy in the face of space-time curvature is another remarkable feature of the cosmic speed limit. It's not just a property of empty space, but a fundamental aspect of reality that remains true even in the most extreme environments the universe can produce. Black holes provide a fascinating laboratory for exploring the cosmic speed limit under extreme conditions. At the event horizon of a black hole, space is so severely curved that even light can't escape. This isn't because light slows down or stops, it's still traveling at full speed, but because space-time itself is curved in a way that all paths lead inward. Inside the event horizon, space and time effectively switch roles. Just as you can't help moving forward in time in the normal world, inside a black hole you can't help moving toward the center. The cosmic speed limit still applies, but the structure of space-time is so distorted that even moving at the speed of light isn't enough to escape. At the center of a black hole lies a singularity, a point where, according to general relativity, space-time curvature becomes infinite. Our current theories break down here, unable to describe what happens when the fabric of reality is stretched beyond its limits. Many physicists believe a complete theory of quantum gravity will resolve these singularities, revealing new aspects of how space, time, and the cosmic speed limit function at the most fundamental level. String theory offers one potential glimpse beyond our current understanding. In this framework, the fundamental objects aren't point-like particles, but tiny vibrating strings. The different vibration patterns of these strings create the particles and forces we observe. The cosmic speed limit emerges from how these strings interact within the fabric of space-time. Some versions of string theory suggest the existence of extra dimensions beyond the three spatial dimensions and one time dimension we experience. These extra dimensions would be compactified, rolled up so tightly that we don't notice them in everyday life. The cosmic speed limit would apply within our four-dimensional space-time, but might manifest differently in the full, higher-dimensional reality. This hints at something profound. The cosmic speed limit might be a property of our particular slice of a larger reality. Just as the speed of sound is a property of air, but not a fundamental limit on all motion, the speed of light might be a property of our four-dimensional space-time, but not a limit on motion through extra dimensions. This possibility has inspired concepts like brain cosmology, where our universe exists on a four-dimensional brain, short for membrane, floating in a higher dimensional bulk, space. Other brains might exist in this bulk, potentially with different physical laws and different values for the speed of light. If we could somehow move through the bulk rather than along our brain, we might circumvent the cosmic speed limit without violating the laws of physics. But there's a crucial catch. If such extra dimensions and brains exist, we appear to be firmly stuck on our particular brain. All the forces we know about, except possibly gravity, are confined to our brain. We can't just step off our four-dimensional reality into some higher dimensional shortcut. These ideas remain highly speculative and face significant theoretical and experimental challenges. The cosmic speed limit also plays a crucial role in resolving some of the most perplexing paradoxes in physics. Consider the famous twin paradox mentioned earlier, where the traveling twin ages less than the stay-at-home twin. This isn't actually a true paradox, but a counterintuitive consequence of the cosmic speed limit and time dilation. For a true paradox, consider a rigid rod moving at near light speed. If you suddenly push one end, classical physics would say the other end must move instantly, otherwise the rod wouldn't be rigid. But the cosmic speed limit forbids this instantaneous effect. The resolution: there are no truly rigid objects. When you push one end of a rod, a compression wave travels through it at the speed of sound in that material, which can never exceed the speed of light. The cosmic speed limit preserves causality and resolves the apparent paradox. Another famous thought experiment is the barn pole paradox. Imagine a runner carrying a pole that, when at rest, is longer than a barn. But when running at near light speed, the pole undergoes length contraction and becomes shorter than the barn, at least from the barn's perspective. This means there's a moment when the entire pole fits inside the barn, and someone could theoretically close both the front and back doors simultaneously, trapping the pole entirely within the barn. But from the runner's perspective, the barn is what contracts, becoming even shorter relative to the pole. So how can the pole fit entirely inside the barn? The resolution involves understanding the relativity of simultaneity. Events that appear simultaneous in one reference frame aren't necessarily simultaneous in another. The closing of the front and back doors, which seems simultaneous to someone at the barn, happens at different times from the runner's perspective. The cosmic speed limit ensures that no true paradox occurs, just different but equally valid perspectives. These thought experiments highlight a profound truth. The cosmic speed limit isn't just a constraint on how fast things can move. It's a fundamental aspect of how causality and information flow through the universe. It ensures that effect always follows cause, that the future remains open rather than predetermined, and that the universe maintains logical consistency. But the implications extend far beyond physics into philosophy and even theology. The cosmic speed limit has profound consequences for concepts like determinism, free will, and the nature of time itself. In a universe without a cosmic speed limit, where influences could propagate instantaneously across any distance, the entire cosmos would be entangled in a web of immediate causation. Your decisions now could be influenced by events happening simultaneously on the other side of the universe. The distinction between past, present, and future would break down, but our universe, with its cosmic speed limit, has a different structure. Causality flows like a wave, limited by the speed of light. The universe's past light cone, all events that could have influenced the present, is clearly separated from its future light cone, all events that the present can influence. This separation creates what philosophers call the now, the moment of becoming, where the indeterminate future crystallizes into the fixed past. This structure might be essential for free will to exist in any meaningful sense, If everything in the universe could instantly influence everything else, there would be no local causation, no ability for a system, like a human brain, to evolve according to its own internal logic without immediate external determination. The cosmic speed limit creates protected regions of space-time where local causation can operate before more distant influences arrive. Some philosophers and theologians see deep significance in this structure. The Jewish philosopher Hans Jonas argued that the cosmic speed limit creates the conditions for genuine novelty and freedom to emerge in the universe. The physicist and Anglican priest John Polkinghorne suggested that the universe's causal structure, governed by the speed of light, allows for both divine providence and human freedom to coexist. Whether or not you find these philosophical and theological perspectives compelling, they highlight the profound implications of the cosmic speed limit for our understanding of reality and our place in it. The speed of light isn't just a number in physics equations, it's a fundamental aspect of the universe that shapes everything from causality and free will to the very possibility of life and consciousness. And this brings us back to you, sitting here watching this video. The cosmic speed limit isn't just an abstract concept, it's part of your daily reality. The light entering your eyes right now, allowing you to see these words, travels at exactly this cosmic speed limit. The electrical signals in your brain, enabling you to comprehend these ideas, propagate at speeds governed by the same fundamental constant. Your past, present, and future are separated by light cones defined by this cosmic speed limit. Every cause and effect in your life, every decision and consequence, every communication and relationship exists within this causal structure. You are not separate from these cosmic laws. You are their expression, a way for the universe to understand its own limits and possibilities. The atoms in your body were forged in the hearts of stars that exploded billions of years ago. The light from those explosions traveled across vast cosmic distances at exactly the speed of light, neither faster nor slower. The fundamental forces that hold your atoms together, that enable chemical bonds and biological processes, all propagate at this same cosmic speed limit. You exist because the universe has this particular structure with this particular cosmic speed limit. If light traveled at a different speed, stars might not form, atoms might not be stable, and life as we know it might be impossible. You are not just in the universe, you are of the universe, a complex pattern of matter and energy shaped by the same fundamental laws that govern everything from quantum particles to cosmic expansion. The cosmic speed limit reminds us of both our limitations and our connections. We can never travel to distant stars as quickly as we might wish. We can never see the universe as it is now, only as it was when the light left those distant objects. We can never escape the fundamental constraints of space and time, but these same limitations create the conditions for our existence. The cosmic speed limit helps protect causality, ensures the stability of matter, and allows complex structures like stars, planets, and living organisms to exist. What seems like a constraint from one perspective is actually a foundation from another. And there's something profound about living in a universe with this particular structure. You can look up at the night sky and see stars as they were years or centuries ago, their light having traveled across vast distances at the cosmic speed limit to reach your eyes at this moment. You can send a message to someone on the other side of the world and know that it will travel at the speed of light, neither faster nor slower, regardless of how you or they are moving. In a universe teeming with randomness and chaos, the constancy of the speed of light stands as a beacon of order and reliability. It's the same everywhere, for everyone, at all times, a universal constant in the truest sense. In a reality where so much depends on perspective and frame of reference, the cosmic speed limit provides a fixed point, a shared reference that all observers can agree on. This constancy connects you to the cosmos in a deep way. The same speed limit that governs light from distant galaxies also governs the light reflecting off this screen into your eyes. The same constant that appears in Einstein's equations describing the curvature of spacetime also appears in the quantum field theories describing the particles that make up your body. As you go about your day after watching this video, I encourage you to occasionally remember the cosmic speed limit and its profound implications. When you see sunlight streaming through a window, remember that those photons traveled for 8 minutes at light speed to reach you. When you use your smartphone, remember that the electromagnetic signals it sends and receives travel at this same cosmic speed limit. Remember that this fundamental constant shapes not just the behavior of light, but the very fabric of reality itself. It defines the relationship between space and time, between mass and energy, between cause and effect. It creates the conditions for atoms, stars, planets, and life to exist. It connects you to the cosmos in ways both subtle and profound. The cosmic speed limit isn't just a fact about the universe, it's a window into the fundamental nature of reality itself. By understanding why nothing can go faster than light, you've glimpsed something essential about the cosmos and your place within it. You've seen how the universe's most fundamental constraints are also the foundations that make your existence possible. So the next time you look up at the stars, remember that the light entering your eyes has traveled at exactly 186,282 miles per second, no faster, no slower. And in that constancy, in that universal limit that nothing can exceed, you've discovered not just a law of physics, but a profound truth about the nature of reality itself. The universe has a speed limit, and that limit makes everything, including you, possible. This isn't just a scientific fact, it's a cosmic truth that connects you to everything that exists, from the smallest quantum particle to the largest galaxy. You are part of a universe governed by this fundamental constant, a universe whose very structure is defined by the cosmic speed limit that nothing can exceed. Thank you for joining me on this journey through one of science's most profound discoveries. Please give a thumbs up and subscribe to the channel. And if you enjoyed this video, I am sure you are gonna love this other one on the left side of the screen. What if humans aren't the first advanced civilization to call Earth home? In this video, I explore the scientific possibility that an intelligent species might have developed technology millions of years before we humans even existed. See you there.